Hello everyone, I am Pawan Kumar Sak, PhD scholar from IIT Kanpur. I am the TA for the course of Elements of Solar Energy Conversion. So today is the 8th discussion hour for this course. So till now I have discussed problems on based on the different angles. After that I have covered the shading problems. After that I have shown you few problems on flat plate collector. Today I will discuss few problems based on the single axis tracking system. So let's start with the first problem. The first problem is for a single axis tracking mode, mode 1, derive the general expression for the angle of incidence. Okay, so before starting this problem, I would like to give some information related to the mode 1 tracking system. So in the mode 1, what happened that axis of rotation remains horizontal. And it is oriented towards the east and west. East, west. Okay. Next, what happened that in this tracking mode, the surface is oriented towards the south direction. Next, what happened that in this type of single axis tracking mode, we have to adjust the tracker every day. Okay, and we have to adjust in such a way that the beam radiates normally at the solar noon. So what does that mean? That at solar noon, that is omega equal to 0, what should happen? That the sun radiation should be normal to the surface. It means the theta should be 0 degree. And also it is given in the in this mode that surface is oriented towards the south direction. It means that the surface azimuth angle will be the 0. Okay, so by applying this condition, we can derive the expression for the tilt angle, that is angle of incidence. So the formula for this one is like cos theta t is equal to sine delta multiplied by sine latitude with the cos of beta, that is the tilt angle of the surface, plus cos delta cos L cos omega, that is our angle, multiplied by the cos beta plus sin omega cos delta sin AZS sin beta, and subtracted by the sin delta cos L sin beta cos AZS plus cos delta cos omega sin L sin beta cos AZ. Now what we will do, we will place the conditions that we have implemented for this tracking mode. Okay, so when you will put these values, then what will happen, that this third term, that is sin AZS, it will become 0, So this term will become 0, whereas this cos omega will become 1. Similarly, in the fourth term, what will happen, that cos of AZS, it will become 1, and in the last term cos omega will become 1, also the cos AZS will also become 1. So this, the first term will be the sine delta sine L cos beta. Second term will come out like cos delta cos L. Cos omega will be 1. So after that it will be the cos beta. Third term will be the 0. So then fourth term will be minus sine delta cos L sine beta. And the last term, that will become cos delta sine L and sine beta. So what we will do next, that we will combine these first two terms and the last two terms. So when you will combine the first two terms and take cos beta outside, then what will happen, that in the bracket this will come like sine delta sine L plus cos delta cos L. Similarly, from the third and fourth term, we will take this sine beta outside. Then what will happen? It will come out like minus sine delta cos L plus sine of L and cos delta. So next, this term will become cos of L minus delta. So this one will be the cos beta. This one will become like cos L minus delta. Similarly, this term will become sine of L minus delta. Okay, so next what we can do, that we can combine these two terms and it will come out like, this one will be the cos of beta minus L minus delta, and in the left hand side what was there, that this cos theta t. So what I have stated, that at solar noon this angle of incidence should be 0, so it will be the cos of 0. So by equating you can find that beta should be equal to the L minus delta. So this is the tilt angle of the aperture surface. Next what we will do, we want to find out the angle of incidence, that is theta t. So these values are implemented only for a particular time, that is omega equal to 0, but we have to calculate the angle of incidence for every time. So what we will do next, we will put this beta in this cos theta t equations. So this cos theta t will become, this one will be equal to sine delta sine L cos of L minus delta, that I have replaced by beta. Beta is replaced by the L minus delta. Similarly, we will replace every beta by this L minus delta. So this one will be the second term, cos of omega minus sine of delta cos of L sine of L minus delta plus cos delta sine L sine L minus delta cos omega. And what will happen, that this condition, that we have oriented the this aperture towards the south surface, that will happen for every day. So this condition will be satisfied for every theta t. So that's why this third term will be 0. So what we will do next, that we will take this sine delta outside from the first and third term. Then what will happen, after taking this outside, and this one will be the cos of L, that is latitude, multiplied by the sine of L minus delta. Similarly, what we will do, that we will take cos delta and cos omega outside from the second and fourth term. So in the bracket, it will remain cos L minus delta plus sine L minus delta. So from the first term, this will become sine delta. This will become sine of L minus delta. Similarly, from the second term, this will become cos of L minus delta. So in this bracket, what will happen, that this latitude angle will be cancel out. So inside the bracket, only delta term will remains. So this will become sine delta multiplied by the sine delta plus cos delta, cos omega, and cos delta. So the formula for the angle of incidence will become cos theta t. It will be equal to the sine square delta plus cos omega multiplied by the cos square delta. So this is the formula for the angle of incidence for any time, for a particular day. And you can see from here that it depends only on the angle of incidence, that further depends on the day, and this omega, that is our angle, that denotes the time. So this is the angle of incidence for a single axis tracking mode 1. Okay, so if anyone has any doubt, he can ask. Okay, let's move to the next problem. So in the second problem, it is given that a cylindrical parabolic collector is located at location 44 degree north in tracking mode 2. Calculate the variation in the slope of the aperture plane from 8 hours to 12 hours at hourly intervals on 21st June. So in this problem, it has been asked that you have to calculate the slope of the aperture, that is beta. Next, that you have to calculate it for hourly intervals. It means you have to calculate it for 8 a.m., 9 a.m., 10 a.m., similarly to the 11 a.m. and 12 a.m. on 21st June. So let's start. So first, in the problem, it is given that the latitude, that is 44 degree, is given. Next, what we can calculate, that this day, that is 21st June, is given in the problem. So what we can compute from this, we can compute the angle of declination, that is delta. So if you are aware with the graph for the delta, then you can memorize that on 21st June, okay, that will be this day, 21st June, this angle of incidence becomes maximum and the value for it is 23.45 degree. This one is for 21st June. Or if you have not able to memorize it, then you can solve it from the formula that is given by the delta is equal to 23.45 sine 360 or 284 plus n divided by the 365, and n you can compute from this date that is given 21st June, and it starts from the Jan 1. So suppose you are trying to calculate it for 21st June, then what you have to do, that for Jan, n will be 31, Feb 28 days, March, April, May, and June. So in June 21, March 31, April will be 30 days, and this May will become 31. So when you will add these, then you will find that this n comes out to be 170, so 172. And when you will put this value, then you will find that this delta becomes similar that I have stated earlier, that the value for it will be a 23.45 degree. Okay, so now let's move to our problem. So in the problem, it is also given that this one is tracking mode 2 type problem. So for tracking mode 2, the formula that has been derived in the lecture. So that's why I'm writing it directly, that tan L minus beta, this will become equal to the tan delta divided by the cos of omega. So we have the value of delta and the time that is varying from 8 a.m. to 12 a.m. So for every hour we can calculate the hour angle. After that we can place it in this formula and we can compute the beta angle. So let's start with the time at 8 a.m. Okay, so for 8 a.m. the omega will be the, so as you know that this omega compute from the solar noon time. So solar noon time is 12 a.m. So before that what we have to take? We have to take negative sign, and how much hour? So before 12 a.m. there are 4 hours before 12 a.m. So and in every hour the earth rotates around 15 degree. So the omega will become 4 multiplied by 15, that will be minus 60 degree. Now using the formula we can put the values that we have calculated, like for delta that is 23.45 divided by the cos minus 60, and after that this one L is also given in the problem, that is 44 degree. So 44 minus beta, and when you will solve you will find that this value comes out to be so this L minus beta will become equal to 40.94, and this L value is 44 degree, this L value. So from here you can calculate the beta and it will come out to be 4.94 degree. Next what we have to do? We have to calculate the similar for different times, like 9 a.m. So with the time the only variable will be the hour angle. So for 9 a.m. this hour angle will become minus 3 multiplied by the 15, that will be the 45 degree. Similarly you will put values as earlier, this tan 23.45 divided by the cos. Now omega value is minus 45, and when you will solve this you will find that this beta value comes out to be 12.473. Similarly you can do it for 10 a.m. So you have to just change the hour angle value, that is omega for 10 a.m. it will become minus 30 degree. When you will replace it in the formula, then you will find that this beta value comes out to be 17.39 degree. Similarly you can do it for 11 a.m. and similarly for 12 a.m. So at 12 a.m. what will happen? That this omega will become 0. Okay, and for this I am just writing the value directly. This tilt angle will become 20.55 degree. Okay, so that's all has been asked in the problem, that is the slope of the aperture. Okay, so let's move to the next problem. In the next problem it has been asked that a cylindrical parabolic collector is located in Pune and the latitude angle is given and operates in tracking mode 3 on September 17. Find out the beam intensity on this day at 15 hour if the DNI value is given. So what we will see, that what are the data given in the problem. So in the problem The latitude is given as 18.5 degree. Next, the day is given in the problem, that is 17 September. September 17. So what we can do with this date, that we can compute the angle of incidence. So first we have to calculate the n, that will be the 31 plus 28, 31 plus 30 plus 31, this one is for May, plus 30 plus 17, this one is September. Okay, and when you will add all these terms, you will find that this n comes out to be 260. After that, what we will do, we will calculate the declination angle, that is delta is equal to 23.45 sine of 360, 284 plus n divided by the 365. So now we will put the value of n, that is 260. When you will solve this, you will find that angle of declination comes out to be 1.41 degree. Okay, so we have calculated the angle of declination, that is delta, and latitude is given in the problem directly. Next, what is given, that it has been given asked for a particular time, that is 15 hours. So for 15 hours we can calculate the hour angle. So for hour angle, what I have told you, that after 12 p.m. we will take it as positive. So for 15 hours it will be 3 multiplied by the 15. So this omega will become 45. After that, it has been given that the DNI value is 600 watt per meter square. So IN, that is normal radiation. This one is 600 watt per meter square, and we have to calculate the beam intensity. So for what is the formula? For the beam intensity, it is given by the IT is equal to IN multiplied by the cos of theta t, and this theta t is the tilted angle, angle between the normal of the plane and with the DNI. Thus, we have to calculate this angle of incidence, that is cos theta t. So for this, we know the formula for this tracking mode 3. Okay, so I am writing directly the formula for this mode. You can find the derivation for this formula in lectures. Sin delta plus cos L now you can put all the values that are known. So the L value is 18.5 degree, and delta we have calculated at 1.41 degree, plus cos of 18.5 degree multiplied by the cos of 1.41 degree and multiplied by the cos of 45. So this one will be the whole square plus cos square of 1.41 degree multiplied by the sin square of 45 degree, and this one will be the half. Okay, so I'm just writing the values directly as I have calculated all the values earlier. So for the first term, that the whole square term will become 0.4.99, and the second term will become 0.4997. So this one is the cos theta t. So when you will solve it, you will find that this theta t value comes out to be 16.34 degree. Now you have the value for the angle of incidence, and the DNI is given in the problem directly. So from here we can calculate the IT. that will be the 600 multiplied by the cos of 16.34 degree. So it will come out to be 575.76 watt per meter square. So this is the answer that has been asked in the problem. So if anyone has any doubt, he can ask. Okay, so let's move to the next problem. So in the next problem, it has been asked that for the polar mount of single axis tracking, find out the angle of incidence of solar radiation on a solar collector for location of 21 degree north at 11 hours, and the solar time 11 hours solar time is given 121st August. Sorry. Okay. So first, this polar mount, this one is nothing but the mode for single axis tracking system. Why we called it that, I will explain you. So in the polar mount, what happened that the axis of rotation is oriented towards the north and south. So this one is north-south orientation. Next, this axis of rotation, it has been given a tilt angle. Okay. So this axis of rotation will have a tilt, and this value of the tilt, this tilt angle will be the latitude of the location. It means wherever you want to place this single axis tracking mode for, you have to just calculate or find out the latitude for that angle, for that location, and you have to place your tracking system at angle of the latitude. Okay, so by doing this, this tilt angle, when it becomes to the latitude, what happen that in such conditions, the axis of rotation becomes parallel to the axis of rotation of the earth. Okay, so what we can say that, in this condition, the angle of incidence, it will becomes to equal to the angle of declination, that is delta. So in this mode 4, we can calculate the angle of incidence directly. So in the problem, it is asked for a particular day, that is 21st August, and the time is given. But for angle of incidence, it depends only on the day, that is 21st August. So for 21st August, we have to calculate the declination angle, that is delta. So for that, we will calculate n. So Jan 31, Feb 28, March 31, April, May, July, August. So on August 21, it is asked. So when you will sum all these numbers, you will find that this n comes out to be 233. Now you have the value for the n, so you can calculate the angle of incidence. That is given by the formula 23.45 multiplied by the sinusoidal of 360, and it is multiplied by the term, that is 284 plus n divided by the 365. So you can place the value of n, that is 233. This one is 233. Then you will find that this delta comes out to be 11.75 degree. So for mode 4 single axis tracking system, the angle of incidence, it will become directly equal to the angle of declination. So this theta t will be equal to delta, and it will become equal to the 11.75 degree. So that's the answer. Okay. So now let's move to the next problem. So in the next problem, it has been asked that derive the expression for the theoretical limit of concentration factor for a three-dimensional concentrator. Also calculate its value. So first I will try to explain what is the concentration factor. So let's say this one is the aperture and this one is the receiver. So what does this aperture do? It will reflects or transmits all the radiation that is falling on this area to the receiver. Okay, so let's say the area of the receiver is AR and the area for the aperture is AA. So this is the area for the aperture and this is the area for the receiver. Then the concentration factor is given by the ratio of this aperture area and the receiver area, that will be equal to the AA divided by the AR. So this is the formula for the concentration factor. So we have to compute its maximum, that is maximum, or also called as theoretical limit for this concentration factor. Okay, so let's suppose this one is our sun. So what, and this is the aperture that is placed at a distance of r with the center of the sun. This one is r and the area of the aperture is AR and the radius of this sun is small r. So now connect this sun with the aperture. Okay, so this one is not looking correct, but this is the angle, that is 90 degree. Okay, so now what we can say, also let's say the temperature for the sun is Ts. Then what we can say, that the sun radiates let me write that the total radiation from the sun. So we can write it directly using the formula, that is Stephen-Boltzmann law, that is equal to sigma Ts ki power 4 multiplied by the area of the surface, that is 4 pi small r square. Okay, now what we can say, that whatever is the radiation coming out from the sun, it will radiates uniformly throughout the area. So what we can do, that we can assume a circle of radius capital R. Okay, so what we can say, that for this area of radius R, the radiation from the sun will be equal to the 4 area of radius small r. It will equal to the radiation that is coming out for the area of radius capital R. Okay, now what we can say, we can that if we want to calculate the radiation per unit area, then we can say that this radiation per unit area, it will be equal to the sigma of Ts की power 4 multiplied by the 4 pi small r square. It will be divided by the 4 pi capital R square. So this is the radiation per unit area coming out from the sphere of radius capital R. Okay, so now we know that our aperture is located at this location capital R. So we know the radiation intensity per unit area. So if we know the area of this receiver, we can say that the radiation falling on this aperture, let me say that HQ S to R, sun to the receiver, it will be become equal to the sigma Ts की power 4 multiplied by the 4 pi r square divided by the 4 pi capital R square, and it will be multiplied by the area of the aperture. Sorry, I have denoted it as AR. Let me denote it as AA. Okay, so this one is AA. Now what we are assuming, that whatever is the radiation falling on this aperture, that is AA. Okay, it reflects or transmits to the receiver, that is of area AA. So we are assuming a perfect condition that is not possible in real life, as there are many losses while transmit or reflecting this radiation to the aperture. But for theoretical and to calculate the maximum value, we are using this. So we are assuming that this Q from the sun to the receiver is equal to the Q of receiver to the aperture, and it will become equal to the sigma Ts की power 4 multiplied by the small r square divided by the capital R square multiplied by the area of aperture. Okay, now what we will try to find, we will try to find the radiation that is radiating from this receiver. Let me say it as AR. Yeah, correct. So we are trying to calculate the radiation. So the radiation from the receiver, that is Q, is equal to the sigma T of receiver की power 4 multiplied by the area of this receiver. Okay, now what we will say, that this radiation exchange between the sun to the receiver and this receiver to the sun will come out to be in equilibrium when this temperature of this receiver will become equal to the temperature of this sun, that is Tr equal to Ts, or we can say that this Q of sun to the receiver is equal to the Q of receiver to the sun. Let me check that. Yeah, okay, so this one is only theoretically. This cannot happen in practically or in real life. Now what we will do, we will equate these. So this one is QR to the S. Okay, so actually if I will try to find the radiation from receiver to the sun, then we have to multiply it by a factor, that is E r to the us, that is similar to the safe factor that we have learnt in the radiation course. So if we will equate these terms, then what will happen? That this sigma ts ki power 4 multiplied by the small r square divided by capital R square a, and it will become equal to tr ki power 4 e of rs. So this ts and tr are equal, we are assuming. Okay, so from here we can say that this aa multiplied by the ar, it will become equal to the capital R square divided by the small r square multiplied by the e of rs. Okay, so next what we will say, that this ers, that is the fraction of radiation coming out from the receiver to the sun. So the maximum value it takes, it may take 1, but it will always remain less than 1. So for maximum value of this, we are assuming that ers is equal to 1. So this will become equal to the capital R square divided by the small r square. So now we can calculate the maximum value of this concentration factor. It will become equal to the capital R square divided by the small r square. So this is the formula for three-dimensional receiver. Okay, now in the problem we have calculated it, and then we have to calculate its value. Sorry, let me correct it as 3D concentrator. So now suppose we are calculating it for sun and between sun and earth. Okay, so for sun and earth, I am taking this capital R as 1.495 into 10 to the power 11 meters. So this one is the mean distance between the sun and the earth, and we know that the radius of sun is around 6.4 into 10 to the power, so this value is 6.96 into 10 to the power 8 meter. So now we can calculate this CR max. It will become equal to the 1.495 into 10 to the power 11 divided by the 6.96 into 10 to the power 8 ka whole square. So when you will solve this, you will find that this concentrator factor, maximum value of this concentrator factor, it will become equal to the 46,138.5. So this is the maximum concentration ratio that you can achieve, but it's all theoretical. It can never happen possible in practical life. Okay, so that's all are the questions that I want to cover in this discussion hour. If anyone has any doubt, then he can ask. Okay, so that's all for today. Let's see you in the next discussion hour that will happen on 25th September. Sorry, on 24th September. Okay, so thank you for listening.